Hello and welcome to Lab 4. I'm Emma Heller. The goal of this lab was to predict circuit behavior and measure potential differences in the circuit with voltmeters and measure current with ammeters. In analyzing electric circuits, we can apply two rules. First, the loop rule, which states that the sum of all potential differences around a circuit is zero, and then the node rule, which states that the sum of the currents flowing in is equal to the sum of the currents flowing out. Another important topic we cover is Ohm's law, which states that voltage is current times resistance. Since most of this lab was observations, I summarized some of my most important findings I discovered in the lab here. I'll go into more detail about each of these during my presentation. So for the first part, here's a simple series circuit with two 1.5 volt batteries, two resistors, and two ammeters. Using V equals IR, we can predict the current I1 and I2 that would be measured by these two ammeters here. We predicted it to be 0.02041 amps, and our predictions were correct. When the ammeter is connected in reverse, it reads negative 0.02 amps, and this is because the current is flowing in the opposite direction. Next, when one of the ammeters is replaced with a voltmeter, the voltmeter measurement is the combined voltage of the batteries, and so it reads 3 volts, but the ammeter shows 0 because the circuit is open, since current cannot travel through a voltmeter. This is what I got when I added up the voltage from the batteries, 3 volts, and then subtracted the voltage from each resistor, which is a total of negative 3 volts, giving us a net total of 0 when we complete the loop. You can see where I got these values from in my next slide. Here are all the individual potential differences around the circuit. We can use these findings to graph the voltage around the circuit, and this is what we get for potential versus position. The potential difference rises and falls, rising first by 1.5 volts each time from the battery, and then decreasing when you go through the 47 ohm resistors, staying steady when there's no resistance, and then decreasing even more drastically through the 100 ohm resistor. So just a quick question, when you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? This is because current does not travel through a voltmeter, so it will not affect the current. So the ammeter does not change. Okay, onto resistors. In this case, we are replacing the voltmeter with an ammeter in parallel with a 100 ohm resistor and looking at what happens to the current through the other ammeter. Current will travel along the path of least resistance, and since a perfect ammeter has 0 resistance, the current will travel through the path without the resistor. Because of this, the ammeter reading increases from 0.02 amps to 0.06 amps. From my potential difference measurements in part 5 and current measurements in part 6, I was able to calculate the resistance of each of these circuit elements. Here's what I got. Next, we create an RC circuit with a 10 ohm light bulb, a 9 volt battery, and a capacitor of 0.02 farads in series. When the current starts running through the circuit, the bulb is lit. After the capacitor becomes full and can no longer store electrons, the current actually stops traveling through the circuit and the bulb is no longer lit. Next, the capacitor is connected directly to a 10 ohm battery, and we find that the capacitor begins to discharge and lights up the bulb again. So when you removed the battery from the circuit, the current flows in the opposite direction. It should take about the same time to charge and discharge a capacitor with the same amount of resistance, but it should take more time if the resistance is higher, and this is what we examined with the 10 ohm and 20 ohm resistor. The reason that they're not exactly equal is because when we do this lab, it's easier to see when the capacitor is completely discharged than when it is charged. We have a 0.2 farads capacitor, a 9 volt battery, and a 30 ohm light bulb here. The capacitor is fully charged, and then the battery is removed so that the capacitor discharges its current and illuminates the light bulb. We measured the voltage for 20 seconds and graphed out the results on the next slide. So here's the plot of the natural log of change in potential difference over the initial change in potential difference first time, and it should yield about a straight line with a slope of negative 1 over RC, which RC is the time constant of the circuit, the time at which the voltage difference has dropped to 1 over E of its original value. And then we look at, does this computed value agree with the RC value of the circuit? And yes, the slope, because it's equal to negative 1 over RC, we calculate RC to be 5.99 ohm farads, which is just seconds, and our actual RC is 6 seconds, so comparing those values, our percent error is very small. If you had used an actual ammeter instead of an ideal simulated ammeter, then the actual ammeter would have contributed some resistance, so the measured current would be smaller than the actual current. Ideally, if you had used a battery to charge a capacitor with no resistor in the circuit, then the capacitor would charge right away. However, this is not the case in real life. Real wires, batteries, and capacitors contribute resistance, which means that the ideal model would predict the capacitor to reach full charge quicker than it would in real life. In conclusion, the behavior of the circuits that I observed acted as expected following the principles of energy conservation, current conservation, and Ohm's law. I learned how to set up circuits and use an ammeter to measure current and a voltmeter to measure voltage. Finally, working off the what-if questions, I predict that there would be more errors in my measured quantities if I had performed this lab in real life due to equipment rather than the equipment in my simulated lab. Thank you.